Alright, now that we're talking about how arrays work, and especially in C, this is a good time to do one more example that sort of illustrates how this whole thing works a little bit better. So the example that I'm going to do is going to be called prime. And what this program is going to do is it is going to, given an integer, it's going to find that prime number. So if we ask it for the first prime number, it's going to give us 2. If we ask it for the next one, it will give us 3, etc. The next one is 5, the next one's 7. So to do that, we're going to go ahead and include some stuff. Include standard IO, include math, include standard lib. Math is special, so I'll put it at the bottom. And then I'm just going to start. Actually, I'm going to do this sort of main first, just to be clear. So int main, int argc, char pointer argv. If argc does not equal 2, we could print a usage message, but I don't want to. I'm just going to blow up. So we're going to take the nth prime, run a printf, that the nth prime is pp. So now all we have to do is write this prime function. So prime to find the nth prime, we're going to create an array of all of the primes, the first nn primes. So for long, I like initializing my arrays, so we're going to initialize all of these to 0. I don't think it actually matters for this particular algorithm, but we're still doing it. So then the 0th prime is 2, the 1th prime is 3, and then the next one is 5. So then starting at index 3, going up to index n, up to 1 less than n, we're going to go ahead and say that our guess for the next prime is going to be 2 more than the last prime. Whatever the previous one was, we know that after the first one they're all odd, so we might as well skip forward 2. And then while our guess is not prime, we're going to increase our guess by 2. Once we find a prime number, we're going to put that value into the appropriate slot. And then after we go through this for loop, we found the nth prime. It's the one in the last slot of the array. All we need to do is now write a function that checks if a number is prime. Now, conveniently for us, we went ahead and passed our array of all the primes before us to the function that tests for primality. That's a key part of this trick. So we're going to have isPrime returns a boolean, which we're going to spell int here, because that's the traditional way to do it in C. We're going to pass an array of unknown size. That's equivalent to a pointer. And then we're going to pass in the number that we're testing. And then we're going to say for each prime number up to the square root of the one that we're looking for. If we're divisible by that number, we are not prime. Elsewise, if we're not divisible by any of the numbers up to our square root, up any of the primes up to our square root, then we will go ahead and return 1. So now all we need is the square root roundup function. And we have a square root function called square root, but it works on floating point numbers. Mostly we've avoided floating point numbers, but it's much more convenient to just cast back and forth and round than it is to try to write an integer square root function from scratch. So there is our program that is going to deal with calculating prime numbers. So we try to compile it, and we get this error, undefined reference to square root, undefined reference to ceil. And the problem is we haven't included the math library. On Linux, the math library isn't included in every executable by default because it's trying to sort of save space or something, because not every program says square root. So in order to add that library, we have to say -lm for the math library at the end of the command line. So what is the 5th prime number? 5th prime number is 11. What's the 10th prime number? Is 29. 100th prime number is 541. 1000th prime number is 7919. Those all seem reasonable. I'm happy with those outputs. I'm not going to translate this to assembly. Instead, we're just going to explore how C works a little bit more. So we're going to copy prime here to prime 2. And we're just going to make some changes. Specifically, I'm going to change all of the arrays into pointers. We're going to go ahead and say this is a loca. And that means I need to include that aloka thing. Now, just for inconsistency, I'm going to change some of the array references into pointers. So here, we're going to say that this is prime 0. But here, we're going to say that this is the dereference of primes plus 1. And that's going to be prime sub 2. Down here, our guess is going to be the dereference of primes plus I minus 1. Up here, we're going to say that we're going to still take this primes array, but this reference here is going to be the dereference of primes plus II. So we're going to go ahead and compile that. Again, we need the math library. Other than that, the changes that I made compiled perfectly. So prime to 100 gets us 541 again, so that's still the same program. So it's worth explaining a little bit what's going on here. And to explain what's going on here, I'm going to go ahead and create another copy of this called, I'm going to copy prime 2 over to prime 3.c. We're just going to make one more minor change to some of these references. So instead of this being prime sub II, we're going to make this be II sub primes. And instead of making this be instead of making this be primes sub nn minus 1, we're going to make this be nn minus 1 sub primes. Could that possibly work? Is this program still even going to compile? I'm going to make sure to include the math library, and oh yeah, that doesn't work because I got my thing backwards. The indexing operator always goes second. So let's go ahead and just make sure the indexing operator always goes second. Alright, Alright, with that minor fix, this thing compiles. Let's see if it's the same program. Yeah, it's the same program. It still produces 541. So how could it possibly be that 2 primes is the same thing as primes 2? That's simple. The answer is that this is the real mechanic, right? Array indexing is just what we call syntactic sugar. The square bracket syntax isn't a native operation that the compiler actually implements. What happens is that the square bracket syntax gets translated into this pointer syntax. Now the mechanics of pointers is that when you have a pointer and then you add an integer to it, what we're doing is, so pointer plus integer is pointer plus integer times size of pointer type as a memory address. So this is called pointer arithmetic, and it's a way to calculate, it's realistically a way to calculate array offsets. It's exactly the thing that we want for array indexing. But what this means is that this prime 0 is, so primes 0 is dereference of primes plus 0. That's what that means. And now this thing down here, so 2 subprimes is dereference of 2 plus primes. Now, this pointer plus integer operation, sure, it's defined as whatever it works, but why is integer plus pointer the same thing? The reason for that is because the people on the C Standards Committee were completely convinced that it was essential that we have the commutative property for addition. So it doesn't matter what order the two arguments to addition are, you should get the same answer. And that they thought was true even if they're different types. So if addition is commutative, and the definition of array indexing is a translation into this pointer syntax, pointer addition syntax, then necessarily you have to be able to swap the array for the value being indexed in either direction and get the same answer, and that's what's true in C. If you ever want to troll your coworkers at some point in the future once you've graduated, go ahead and translate some of the array indexes into these swapped array indexes, and then carefully don't mention that I suggested that. So that's the last example for today. Good luck on the upcoming homework, and remember to have fun, because that's how you learn things.